Okie dokie. One thing I forgot to mention, we said this is called A13. I should mention that the original matrix, we should be calling the original 3 by 3 here. We should be calling that A. Okay, to make sense of why this is A13. Anywho. Okay, so time for a formal definition of the determinant of any size. Okay, so we'll say let A equal, well, in the top I have A11, and I have A12, dot, 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 say A1N. Then I have A21, dot, 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 A M1, A22, so this is an M by N matrix, sometimes called a generic M by N matrix. How do I find a determinant of such a thing? What the hell? The determinant of A is, well, you use the first row like we usually do, right? You go A11, then you go A12, and so on and so forth until you get to A1N, which we'll put over here. Now, instead of doing that whole plus minus thing, what we're going to do is combine. So let's look at what we had above. We had the, so here was A11, and then we had a determinant sitting there, and we also had a plus or a minus in front. Okay, what we're going to do is we're going to take this determinant, and we're going to take this plus or minus, and combine it into a single factor, which we will call C, well, C11. And we're actually going to go with pluses all the way. No, we're not going to alternate, because what we're going to do is we're going to keep these all as pluses, all pluses, and the alternating thingamabob that's happening, we're going to have that happen inside these C values. So we're going to define the C. C I J is, well, to get the plus minus thing, we're going to use this I -1 to the I plus j. And then we're going to multiply by an appropriate determinant. Okay, so again, what we had before in the two examples I did and the exercise is you had this plus minus, plus minus, plus minus. That is done with this factor here. And then you have the determinant multiplying. So if you think about it, this is where we get this diagram from. For example, if you have 1, 1, I and j are both 1, then you have -1 squared, which is plus 1. And if you have I is 1 and j is 2, then you have -1 cubed, which is the minus here. Anyways. Okay, we have a very excuse me, a very useful theorem, the first of many. Useful because you're probably noticing after doing a few determinants that this can be very time consuming, right? So we're going to have some theorems that help us save time. Theorem 1 says that, let's back up before I do a Theorem 1. Okay, we give a name to this. This is called the cofactor expansion. Cofactor expansion across the first row. And the word cofactor is coming from, where should I put this? That's this thing. It's what's called a cofactor. The Cij is called the Ij in brackets Ij cofactor. So this expansion, this plus this sum, this big sum is called the cofactor expansion across the first row. And then this Cij is called the Ij or ijth cofactor. Okay, Theorem 1. One more thing before Theorem 1. I'm just realizing I made a boo-boo here. Okay, we define determinants only for square matrices. So I shouldn't be using an M here. I should be using an N. So scratch out that M and put in N. See if I can. No. So it should be a square matrix. So sorry about that. N. So please fix this in your notes. So this is an N by N matrix. So again, determinants only defined for square matrices. Okay, let's finally do Theorem 1. Okay, so here we said first row. So Theorem 1 says we can use any row or any column. Let's say the cofactor expansion is always the same. This is a bit surprising. It's quite, there's some complication here. You have a cofactor expansion up here. You can think of it as a polynomial where the variables are, not x, y, z, but the variables are all these, n squared variables. And this polynomial has certain properties. And here's one of them. So let's do an example. Let's do this determinant. that we just did. Let's do it again. 5, 6, 5. So let's do this again, but now we're going to use the, use the second column. Let's be more precise here. Let's say do a cofactor expansion down the second column. Let's do that. So I'm going to use the second column in the same way I was using the first row. So second column, take this guy. And what do you get? You get some things. You have a 6, and then you have another 6, and then you have a -2. Now, when you take the first 6, you have -2, 2, 4, -2. And then when you take the second 6, you have this thing jobber. And then when you have the -2, that's that guy down there. -5, -2, 5, 4. Now, what else? Let's remember our useful little diagram. We're using this column. So we go minus, plus, minus. Okay, let's pause here. Very easy to make a mistake. So I'm going to pause and double check everything I've done here. So just going through and redoing everything mentally and see if any alarm bells go off. Okey-doke. Looks good. -6. 4 minus 8 is -4. Plus 6. 10 minus 10 is 0. 10 minus 10 is 0, yes. -2. -20 plus 10. -20 plus 10. -20 plus 10, yes. So we get 24 -20. And we get, as expected, we get 4 again. Okay, this is not coincidence. This is what Theorem 1 is telling us, is that you can use any row or any column, do a cofactor expansion. You will always get 4 if you are careful. If you are not careful, then you will, well, who knows?